if we have an incompressible fluid, there's a really useful principle we can apply called Pascal's Principle. A change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and to the walls of the container. What does that mean? Well, let's look at it right here. That says that, for example, we have two reservoirs of water or fluid, like they're just some fluid, okay, an incompressible fluid, and they're connected by this little channel right here, okay. So, and they have pistons at the top of these reservoirs of fluid, and we can apply a force to the top of those pistons. So let's say over here on this left piston, we apply a force onto it, and it has some cross-sectional area. So we are applying a pressure over here on this piston. And so this statement here means that the pressure that we have applied to this fluid over here with this piston is the same as the pressure applied over here to this reservoir of fluid, okay? So P1 over here has to equal P2 over here if we have an incompressible fluid, okay? And we know that pressure is equal to the force over area. So the force I apply over here over the cross-sectional area of this piston head has to equal the output force over here divided by the cross-sectional area of this piston here. So what happens is that if I can push down and apply a force, we apply a pressure on this side to the fluid, that same pressure has to be exerted over here on this bottom of this piston here to push something up, okay? And so then you have a ratio of the forces and the areas of these pistons, and that comes about because the pressure on this side has to equal the pressure on the other side. And this only works again if you have an incompressible fluid. This is the principle that governs everything that has a hydraulic system. You've got a hydraulic fluid that's incompressible. You push on it in some direction in some part of the system, and then you push on it with some force in some part of the system, and then you create an output force at some other part of the system. So also car brakes work like this too. So Pascal's principle provides a mechanism for increasing or decreasing an applied force just by changing the areas over which these forces are applied. This is another important point that we're going to use in another problem in a minute, that a connected liquid in hydrostatic equilibrium rises to the same height in all open regions of the container. So if you have one container of a constant density, no matter what the shape of the container, the fluid on either side of the container should rise to the same height. So here we have, let's just say this is water inside this unusual container. One side of the container has a larger opening cross-sectional area, and then the water is free to move through here, and then we've got a smaller cross-sectional opening over here. And both of these are exposed to atmospheric pressure. So no matter what the shape of the sides, either side of the vessel, the liquid will always rise to the same height on either side. If you, again, you have the same density of liquid throughout, okay? And then another important point is that in hydrostatic equilibrium, that means we're not moving around. The pressure is the same at all points on a horizontal line through this connected liquid. So you have to have, the pressure would be at the same pressure right here on this side of the vessel as the pressure would be over here. So the pressure here would be the same as the pressure here, and so on. So we can use that principle in order to solve some interesting problems. Gas is compressible, our atmosphere is compressible. So the air in the atmosphere becomes less dense with increasing altitude. So as you go up above the Earth's surface, the atmosphere, the air becomes less dense. 99% of the air in our atmosphere is below 30 kilometers above the Earth's surface. And the atmospheric pressure varies with altitude and with changes in the weather. But the approximate atmospheric pressure at sea level, we call 1 ATM, 1 atmosphere, And that's equal to, well, here I've written 1.013 times 10 to the 5 pascals, but usually for a problem that we're solving, we can just say 1.01 times 10 to the 5 pascals is something at atmospheric pressure. That's just the air in the room that we're sitting in. Here's a few pieces of terminology that are going to be important for us. Something called gauge pressure and something called absolute pressure. These come when we're thinking about pressure measurements. Gauge pressure is the pressure relative to atmospheric pressure. Gauge pressure is positive for pressures above atmospheric pressure and negative for pressures below it. Then absolute pressure is the sum of the gauge pressure and the atmospheric pressure. There are two devices in particular that measure pressure that we're going to talk about here. One of them is called a manometer. And how does a manometer work? Well, here we have a chamber filled with gas at some pressure. We're going to call that P gas. And then we have it connected to this tube right here. The tube is filled with a column of mercury or some liquid. Let's just say maybe it's a column of liquid mercury, okay? And so we've got the gas pressure, the pressure from the gas, and the gas is filling in through this tube right here. And then we've got our column of liquid right here. And since pressures on a horizontal line are equal, the pressure here at the interface between our gas and our liquid must be the same as this pressure right here, P2, which is the pressure that this column of mercury is experiencing over on this side. I could draw another horizontal line here too. The pressure at this side has to equal the pressure over here. So P1 is our gas pressure in this problem. P2 is the pressure at depth of D is equal to H, this depth right here, where we've drawn that horizontal line here, and our column of fluid extends up a height H on this side, okay? And so P1, again, has to equal P2. So that means that the pressure of the gas right here has to equal the atmospheric pressure that's pushing down on this end of our column of fluid that's open to the atmosphere, plus the pressure coming from this column of liquid above this point right here. And the pressure coming from that column of liquid is rho gh, the density of the liquid times gravity times the height that this liquid is above this measurement point that we're taking. Another device we can use to measure pressure is called a barometer. A barometer measures the atmospheric pressure. So if you hear anybody talking about weather and barometers, this is what they're talking about. So here's an example of how a barometer works. We have a glass tube right here, and it's filled with some liquid. And it is then inverted and placed in a beaker of liquid of the same fluid. Some, but not all, of the fluid leaks out of the tube. And so what you have here is this column right here. Let's imagine that it's mercury. We've got this column of mercury right here. And then we are sitting it in a vat of mercury as well, okay? And so we have this part of the mercury sitting in the dish is exposed to the pressure of the atmosphere. So you've got the pressure of the atmosphere pushing down on this exposed fluid. That pressure has to equal the pressure at the same level inside this tube filled with liquid here, okay? So out here at point 1, we have the atmospheric pressure pushing down, okay? And here at point 2, we have the pressure from this column of fluid pushing down on this point right here. So we have that the pressure of the atmosphere outside the tube has to equal the pressure coming from this column of mercury, which is going to be the density of mercury times gravity times the height of this column of mercury. So if there's some weather event and the pressure in the atmosphere increases, then this is going to change the height of the column. Or if the pressure of the atmosphere decreases, this is going to change the height of the column. Okay, and so another unit we can use to measure pressure is what we call a millimeter of mercury. That's this mmHg. And it comes from this experiment right here, or these barometers right here. 1 millimeter of mercury is the same as 133 Newton per, let's just say meter squared, not meter sub 2. 133 Newton per meter squared is the same as 1 millimeter of mercury. It's just another way to measure pressure. Now, 1 atmosphere is equal to 760 millimeters of mercury. That comes about from this, again, experiment too, that originally when barometers were created, they were created with mercury, and for standard atmospheric pressure pushing down right here, they found that the column of mercury inside this tube here rose to a height of 760 millimeters. And so that's why we say that 1 atmosphere could also be measured as 760 millimeters of mercury. So 760 millimeters, that's the same thing as 76 centimeters, that's 0.76 meters. So gotta have a really long tube, I guess, for 1 atmospheric pressure to give you 760 millimeters of mercury. We're going to use these ideas in order to solve this problem here, which we usually solve in lab, but it requires more than one person to be able to work together, so we can't do it this year. We have a U-tube, a tube in the shape of a U, that contains 2 liquids in static equilibrium with each other. One of those liquids is oil, and the other liquid is water. And at the ends of the tubes are both open to the atmosphere. So on either end of the tube, that fluid is going to be exposed to air of atmospheric pressure. Here I have my U-tube. I've got the oil in the left, and I've got the rest of it in water. Okay, the blue is the water, the yellow is the oil. Now, if we filled this tube entirely with water, the height of the fluid on the left would equal the height of the fluid on the right. But we have fluid of a different density, the oil, that we've put into this tube as well. And so then the fluids adjust to a new equilibrium. They're adjusting so that the pressure at the same height in the fluid equals each other on either side of this bend in the tube. So the pressure over here at point 1, we'll call P1, has to equal the pressure over here at P2. So I'm using my reference point as the interface here, where we have the interface between the water and the oil. Now we know a few more pieces of information to help us solve this problem. So this column of water on this side right here, I'm going to call that L. Okay, and we know that L is equal to 135 millimeters. And then we know this distance D right here. So D is the distance between the height of the oil column and the height of the water column. And then that quantity is equal to 12.3 millimeters, okay? And with that information, we have enough to figure out what is the density of this oil, okay? And so to find the density of this oil, we have to use the principle that the pressure at point 1 has to equal the pressure at point 2. P1 is equal to P2. Now on both sides, the top of the column of fluid is exposed to the atmosphere. So you've got atmospheric pressure on both sides, okay? Plus, for our column on the left, we've got the pressure coming from that column of oil. So I'm gonna call that the density of oil times gravity times the height of the oil, because remember, we can say that pressure is equal to rho g h for a column of fluid. And then on the right side, we've got plus the density of that column of water. And that's going to be rho water G times the height of my water column, okay? And so, well, we see that we've got the atmospheric pressure on both sides of the tube, and then those would just cancel out from each other. So we have, oh, and G also cancels out from each other on both sides. So we have rho of the oil times the height of the oil column must equal density of the water times the height of the water column. So density of my oil equals density of water, height of the water column divided by the height of the oil column. Okay, so that height of that water column is going to be the height L, and then we're going to divide it by the height of our oil column. So we were just given these quantities of D and L, but then the height of that oil column there is just going to be our quantity D plus our quantity L. Okay, so then our density of oil will equal to our density of water, which was 1,000 kilograms per meter cubed, times the height of this water column from my reference point, which was 135 millimeters. And I'm going to divide it by my 135 millimeters plus my little quantity D here, which is the difference in the height of the oil column and the height of the water column from our reference point. And so that distance was 12.3 millimeters. And it's okay that I use millimeters instead of meters because the units of millimeters are going to cancel on top and bottom here. So then this tells us that the density of the oil column, or the density of this oil in our experiment here, is 916 kilograms per meter cubed, only a little bit less dense than water. Well, let's talk about pressure in our human bodies. Our bodies experience pressure all of the time. Well, let's think about the increase in pressure between the heart and feet of a person. So that increase in pressure is equal to the density of our blood, if we're thinking about the blood pressure, times gravity, times the difference in height between our feet and our heart. So we've got the density of blood is 1,050 kilograms per meter cubed times 9.8 meters per second squared times, I'm just going to say an average person has a distance between their feet and their heart of 1.4 meters. And together that gives us a pressure difference between our feet and our heart of 1.4 times 10 to the 4 pascals. If you're someone who's on your feet a lot or someone who sits a lot in a chair and you don't move around too much, you can really increase this change in pressure between your heart and your feet, and that's not really a good thing. But you can try to reduce this change in pressure by wearing compression stockings. And I have this exact pair that I wear when I'm on very, very long flights. I found that once I got past the age of 30, that when I fly long distances, that my feet will start to swell up. And that's because of an increase in pressure difference between your heart and your feet. And you can reduce that by wearing these compression stockings. And that's why my grandma has to wear them too, okay? We can also experience a change in pressure on our eardrum whenever we fly or whenever we go swimming. Here's a cross-section of our ear, and there's a little pocket of air here behind our eardrum. So this pocket of air doesn't equilibrate very rapidly with the air, the atmospheric pressure that's coming from outside pressing on the eardrum from outside. Okay, so you've got this pocket of air inside your eardrum, this pocket of air or water outside your eardrum, and it takes them a few minutes to become in balance with each other. Okay, so whenever you take a quick dive underneath, underneath the water, you have the inside your ear here, you've got that pocket of water at atmospheric pressure, but outside your ear here, you've got the atmospheric pressure plus now the pressure of that column of water above you. So your eardrum is going to experience a change in pressure. And so that change in pressure acting on your eardrum is going to equal, if you're swimming, the density of water times gravity times the height or the distance underneath the water surface that you are. Okay, so we've got the density of water, 1,000 kilograms per meter cubed times 9.8 meters per second squared times, let's say we've taken a dive to a depth of 5 meters below the surface of the ocean. And in that case, the pressure difference on our eardrum is 4.9 times 10 to the 4 pascals. And we can remember that pressure is equal to force over area. and solve that for the force that's pushing on your eardrum. And then that force is going to equal the area of your eardrum times this difference in pressure. And we can approximate the area of the eardrum as being 1 centimeter squared, which is also 1 times 10 to the minus 4 meters squared. So if we plug that in here for the cross-sectional area of your eardrum, multiply that by your change in pressure, you've got a pressure acting on your eardrum of 5 newtons. A similar thing happens when you fly in a plane and you get that discomfort in your ear when you're flying a plane, because in that case we're experiencing a change in pressure because we're going up in the Earth's atmosphere, and as we do that, the pressure diminishes actually as we go up in the Earth's atmosphere.